Hi, my name is Lyude, and I am going to be presenting on Rvkms and KMS drivers in Rust. Um, so mainly what I'll be talking about is a general overview of Rvkms and the bindings we have so far, and also sort of an honest opinion on what I think of Rust and why I kind of think it's a game changer for the kernel. And I won't be talking about memory safety, but we'll get into that in a little bit. Um, how did this start? The main thing was we've been working on a new NVIDIA kernel driver, Nova. And Nova is written in Rust particularly because NVIDIA's GSP firmware doesn't have a stable ABI, and trying to handle this in C is pretty hard. We got the inspiration from Asahi, who uses a very similar approach to handle unstable ABIs with their firmware. And we also think that through upstreaming Rust drivers, we can prove Rust's readiness, and projects like Asahi can end up having an easier time being able to upstream their work. So, of course, device bring up for a new driver is pretty difficult, and it takes quite a lot of time. And we also have to be able to write all the Rust bindings that we actually need to get the kernel driver running. Luckily, a lot of this has already been done in RVKM or in Asahi. So there's a lot of bindings we can reuse, and we really just have to work on, upstreaming them and figuring out the things that need to be changed. Surprisingly, though, one of the notable exceptions of this was kernel mode setting. Asahi's kernel mode setting driver is pretty much one of the only parts of the driver that's actually written in C. So there's not any pre-existing KMS bindings for us to actually write a driver against. Nova's way too early in development to be able to have a KMS driver written for it. So, but like KMS was a large enough surface that we wanted to be able to work on this sooner than later, and ideally in parallel to the rest of Nova. So we decided while Nova was getting ready that I would try to port a KMS driver into Rust to try to come up with a set of bindings. And we ended up choosing Rvkms because it's a pretty simple driver. It doesn't require any specific hardware. And yeah, it's so quick explanation of what Rvkms is. It's a virtual KMS driver, meaning it pretends to be a display device. It's also capable of CRC generation, and it also supports write-back connectors. So Rvkms, of course, is the Rust port of the Rvkms driver. It's very early in development driver-wise, doesn't do a whole ton yet. Basically, all it really does is register a KMS driver and set up VBlank emulation using high-resolution timers in the kernel. Eventually, we're going to have CRC generation, hopefully, along with connector write-back, but despite all of this, and despite it being very early in development, it's been very useful in making progress with these bindings, and I think we've actually come a pretty long way in that regard. I also did my best when working on these to sort of structure the API around not just Rvkms's needs, but also what I've seen from other drivers like i915 and Nuvo. But I would definitely say a lot more time went into the bindings than the actual Rvkms driver, of course. It's pretty small at this point. But yeah, it's worked pretty well. So my main goal with the KMS bindings was, of course, prevent undefined behavior or safe code, of course. Make incorrect KMS API implementations nearly impossible. Rust gives us a lot of tools to actually be able to prove that the way things are implemented are correct at compile time. And we wanted to take advantage of this, but also make sure that we're ergonomic, right? We want to make sure we protect from mistakes, but we don't want to make code messier, inflexible, or more difficult to write. And also as well, one of the things that sort of was brought up by Seema is trying to make sure we limit conditional handling only where it's needed and only where it really makes sense, since that's a big part of the ergonomic issue. So one of the things that sort of brought up is the ability to subclass objects. We'll talk about a little bit what that means shortly. And outside of this, we also wanted to make sure that we only really supported atomic. We'll probably have some basic support for the various legacy helpers. that provide compatibility APIs for user space applications still using legacy mode setting. But yeah, it's atomic only, and we don't really want new legacy mode setting drivers. So these bindings work on top of the DRM bindings from Asahi and Danilo. Additionally, there's quite a number of other dependencies, but there are quite a lot of differences with Rvkms bindings versus in C. For instance, unlike in C, Rvkms bindings are mostly in control of the order of operations during device registration. And we provide basically a single trait that a driver will actually implement in order to support KMS. And that sort of handles calling things in the right order, registering the device, and that sort of thing. This trait currently has two main parts: mode config info, which basically fills various static information in the mode config structure. This is stuff like the minimum, maximum resolution, various cursor capabilities, and etc. And then create objects, which basically gives you access to a special unregistered KMS device type. This type allows creation of static mode objects like CRTCs, planes, that sort of thing, and non-static mode objects such as connectors can also be created here. In the future, we'll probably add hooks for customizing what happens during the initial mode set. This would normally be used for things like reading back hardware state. So if you want to do fast set, you turn on your computer and it doesn't do a mode set when you get to the login screen. But since we're a virtual driver, we don't really have any state to read back. So for the time being, we just kind of call DRM mode config reset and reset the whole display state to being blank. So one of the neat things is drivers implementing the KMS trait get a KMS driver trait implemented automatically. And this is nice because it actually lets us make it so that KMS-specific methods are only available to devices that actually implement KMS. This is really advantageous because it basically allows us to, from all of our bindings, assume KMS is set up and always there, instead of having to handle, runtime checking, like did they set up v-blanking or did they set up this specific feature. We're able to do most of this at compile time. And of course, that avoids returning quite a lot of options in places where they might not necessarily make sense. So the first part of this is mode objects. DRM sort of has a concept of a mode object where it's basically a object that is exposed to user space through an object ID. It might have a ref count, but it might not, and it can be created at any time. Ones without ref counts can only really be made before registration, though. They also have properties, but we haven't really gotten there in the Rvkms quite yet, so not going to really go over that very much. For implementing these, we have a mode object trait, which for ref counted objects, it's pretty easy. Ref counting fits pretty nicely with Rust's lifetime requirements, and we provide a trait that these objects can use to basically reuse the same kind of like mode setting reference infrastructure that all the other objects are using, since it's basically the same for all of them. Static objects, on the other hand, are a bit more challenging. So static objects will typically share the lifetime of a device, which is not easy to directly map to a lifetime in Rust. A lot of objects are like this, like CRTCs, planes, and encoders. But to work around this, we provide the static mode object trait and something called a KMS ref. Basically, KMS ref acts as a reference count on the parent device while providing access to the static mode object. So it basically fulfills Rust's lifetime requirements and allows owned objects of references to static mode objects. We may eventually replace this with Danilo's DevRes type in the future, but that is currently unclear quite yet, or right at the moment. So implementing things like planes, CRTCs, etc., was a bit more complicated than one might expect. Very few drivers use these structures unmodified. You might recall that I mentioned subclassing, and this is sort of where this comes into play. because more often these objects are embedded within driver private structures. For instance, with VKMS, we have VKMS CRTC, which implements a DRM CRTC. Usually, these additional structures contain various private driver state. So this can be display state that might need to be tracked outside of a single atomic commit. It might also be static driver information like port capabilities, port mappings, and so forth. As well, a lot of drivers often will have more than one subclass of an object. Both I915 and Nuvo are pretty good examples of this. So you might have different classes, for instance, different types of connectors, different types of encoders, and so forth. So luckily, this is not the first time we've had to do something like this in the kernel of Rust. Asahi actually had to do something quite similar for gem bindings. In gem infrastructure, this sort of thing is also very common, where there might be driver private data that you have to keep with an actual gem object. So luckily, it was a little less variable than KMS, since KMS kind of does subclassing a lot harder, but it was still a very good starting point for actually getting this working. So on the actual Rust side, this is done with a number of traits: driver plane, driver CRTC, etc. And a driver is allowed to have multiple implementations of these traits, so to be able to handle multiple different subclasses. Driver data can be stored in them in two ways. The first is being able to pass immutable data to each object's constructor. So if a device has to do some sort of dynamic probing as it's loading, you're able to actually pass whatever information that you need into the structure via that entry point. And then, of course, the other point is send sync containers. So this is basically just any kind of thread-safe lock, a mutex, a spin lock, etc. So in KMS drivers written in C, drivers will typically switch between a common representation and a subclass representation. So this goes sort of back to the DRM CRTC and VKMS CRTC thing we mentioned before. There's a couple of reasons for this. Sometimes you have operations that you want to apply to all different mode objects, regardless of type or only specific types and so forth. In order to handle this, we have two different types of interfaces, a fully typed interface and a opaque interface. And we do the same thing for atomic states as well. And the idea is that you can sort of switch between these two types at runtime. So if you don't need access to driver-specific data, you would use an opaque type. Otherwise, you'd convert it to a fully typed connector. This is done fallibly at runtime. We do have some infallible conversion operators that you can use if you have a simpler driver where you only have like a single implementation. But yeah, this also required us to actually add something so that we could get consistent vtable memory locations, which is not something that Rust has by default. Constants are basically treated more as inline constants rather than actual static constants. But luckily, thanks to some of the work that's been going on, we actually have a macro for implementing this now. So the one thing that's not entirely figured out here yet is if a driver needs further classing. For instance, I915 has more granular subclassing when it comes to a lot of its mode objects. Things like Intel connector are sort of like an upper level representation of an object, whereas you would have like Intel HDMI, Intel DP, and that sort of thing to sort of represent the different types of connectors that you would have. And occasionally you want to be able to go through, you know, in various hooks to work on specific subclasses like that. So I'm hoping this will be pretty easy to just do through Rust's trait system, but it's still sort of to be determined at this point. Now, then we get to atomic commits. Things diverge a bit when we get here because Rust's data aliasing rules say that you can only have one of these at any given time, infinite immutable references or only one mutable reference. So if every atomic check, update, and so forth callback only affected the given object in question, this would be pretty easy. But a lot of times this isn't really the case. A lot of drivers will iterate through the state of other objects in their atomic callback, not just the object that the callback actually belongs to. So I originally tried implementing this using just references, but it worked out pretty poorly. A good example is, let's say you're in an atomic check for a plane and you want basically to go through other objects in the atomic state overall. You already have a mutable reference to the plane state, which means that that plane state is taking a mutable reference from the atomic state. But how do you iterate through other objects then? You've already taken an immutable reference, and you can't really take another. And you can't take an immutable reference either, of course. So the second time through, I decided to take some inspiration from RefCell. This is a Rust API for handling situations where the data aliasing rules aren't exactly ideal. Immutable and mutable borrows still exist, and they sort of have the same rules, but they're checked at runtime instead of compile time. And this also means you're actually able to use them through immutable references, which we use here. So basically, for the atomic state, you're usually working with it through a container called an atomic state mutator. And basically, you always have immutable references to this container, but this container sort of handles doing the bookkeeping at runtime and handing out borrows of atomic states that you want to modify or inspect. So you can only have one borrow for each state at a time, but you can take out multiple different state borrows at the same time, which ends up covering most of the cases that we would actually want to cover. Borrowing is fallible, but we're still able to make this pretty ergonomic. So for instance, atomic check callbacks will pass a pre-borrowed copy to the new state, for instance, so that you don't have to borrow a new one. And we'll also be implementing iterators as well that allow you to iterate through various unborrowed states in the actual atomic state. This works pretty well because most drivers, if they are modifying other objects in a specific objects like atomic check or atomic commit, so forth, they're going to be iterating over other object states. So the types that we use for this are borrowed CRTC state, like borrowed plane state, and so forth. And these have the same sort of separation where they can be used with fully typed states or they can be used with opaque states. So this brings us to the atomic commit composer. Basically, actually that's supposed to say atomic state composer, but basically this is supposed to be a wrapper around a atomic commit mutator. It represents an atomic state that hasn't finished the atomic check phase. And it's basically the same thing, but it also allows you to add new objects into the atomic state. So we can actually restrict adding new objects to only happen within atomic check callbacks where it makes sense. And this can also, in theory, easily be used for allowing drivers to perform arbitrary commits in kernel. So basically, you would be able to create an atomic state, take out a composer and use it to do something, for instance, like enabling CRCs, where you might have to do an atomic commit in order to actually turn them on. So then we also have high-level commit callbacks. There's only a few of these so far, but the main example is atomic commit tail. These have some pretty interesting constraints because for one, there's certain orders of operation that you can put in these that wouldn't make sense that you don't want. For instance, CRTCs can't really be enabled in a commit before they're disabled in that same commit, because physically that doesn't make sense. Because a commit's only supposed to do basically one state change at a time. And we have to ensure that the state as well can't be mutated once it's made visible outside of the commit context. So this is the point where a driver calls commit hardware done. And this is sort of on us because DRM doesn't really know the state of borrows. It can't tell if we have a mutable borrow of a state taken out once we call atomic commit or commit hardware done. So we have to handle all this on the Rust side. And breaking any of these requirements would result in undefined behavior, which we don't really want. But luckily, this comes up with a really cool feature of Rust, type state patterns. These aren't entirely unique to Rust, but they're not typically common in other languages, and Rust generally makes it a lot easier to work with than other languages. This sort of allows us to encode the runtime state of something into compile time state. We've already actually used two here, for instance, the atomic state composer and the atomic state mutator. There are the correct names, okay. But we also have unregistered KMS device, which eventually gets translated to device. And basically the idea is you're representing an object at every portion of its lifetime as a different type. And this allows us to have a very powerful tool for actually enforcing API correctness, which sort of brings us back to the atomic commit tail. This is basically another atomic state wrapper like the atomic state mutator and atomic state composer, but it is basically one that you have to implement yourself if you want to override it. And it lets you control in which order commits happen. And we're actually able to do this safely while being able to enforce some of the more complicated requirements that I had mentioned before. Most of this is done using tokens, where we have a token that represents each step of the process. And in order to get to the next step of the process, you have to provide that token in order to prove that you performed necessary operations. Some examples that we have here are, for instance, with committing mode set enables and disables. You have to call commit mode sets disables, which gives you a ready token. Then you go to the enables, where you pass basically that disables committed token to prove that you passed that step. And then you get a token enables committed token that you can pass later on to that third point there, commit hardware done. And same thing happens with plane updates, where you get a token that says you can perform the updates now. You get a token once you perform them. And you take both of these tokens and you actually provide them to commit hardware done to basically prove that you performed all of those steps. Now, this can be trivially expanded, of course, for more fine-grained control, because many drivers may have to control the specific order in which certain CRTC commits are performed, or certain plane updates, etc. And it shouldn't be too hard to actually expand it to allow for this. But what's cool about this is it lets you make it impossible to write an incomplete atomic commit tail that actually compiles. You have to perform every step and you have to perform them in the correct order. Otherwise, your code just doesn't compile. And every step also takes a mutable reference to the atomic commit tail, which means that if you were to have to take out a atomic state composer, or atomic state mutator, you wouldn't be able to mix it with those steps or cause changes to happen until you've actually performed those changes and no longer have other mutable borrows of the atomic commit tail object, which is pretty nice because it allows us to make sure we're still enforcing Rust's data aliasing tools without rules without necessarily limiting what you can do with them. So optional driver features are sort of the next part of this. KMS drivers have quite a lot of features that are optional. A really good example of this is VBlanks. Everything uses VBlanks to some extent, but not all hardware actually has a VBlank interrupt. And sometimes it needs to actually be emulated by the DRM core. So can we gate these features just like we do with KMS driver? Like, for instance, make it so that if your driver supports hardware VBlank interrupts, you're able to call those methods related to hardware VBlank interrupts, but not otherwise if you don't have support for that. And turns out we can do this. We just add more traits. So VBlank support is pretty much the example for this. If you have a driver where you support hardware VBlank interrupts, you basically just implement this trait on a driver CRTC, and it will expose all of those methods by automatically implementing the driver CRTC vBlank trait, and so forth. And we can expand this same pattern to any optional piece of functionality, basically. And since we already control the driver initialization and registration process, it's pretty trivial for us to handle without the user having to do it themselves. So, of course, not much to go over here. You implement the traits, you get the support, and so forth. I'm going to go into the next part of the presentation, but real quick, I want to give a special thanks to the Asahi project because a huge amount of our work depends on their bindings. Myra Canal, because they also committed quite a few bindings that our driver takes advantage of as well. And of course, also my coworkers, Daniello, and everyone else who has been working on the Rvkms driver, like Dave Arley and so forth. But yeah, so my experience with Rust. I sort of want to go over this first to say I won't be talking about memory safety. I think one of the big mistakes a lot of people make when they're trying to advocate for Rust is focusing entirely on memory safety. The thing is, we kind of all know that C is unsafe, that it's a problem, and that it's sort of a problem that's inherent to C. I think a lot of times what people don't realize is when you focus on this point too much, you sort of come across as talking down to a lot of kernel developers because we kind of already know this. And it was honestly a reason that I had actually avoided touching Rust for quite a while. But so if you want to hear more convincing arguments that aren't really centered around this, this part is definitely for you. So yeah, the first thing I sort of noticed is Rust can be a kernel maintainer. Maintainers don't scale, and being a huge part of being a maintainer is trying to stop bad patterns in code. This is pretty time consuming though. It requires you to re-explain yourself repeatedly and hope you didn't miss something. It can make you snippy, can burn through your motivation, and of course that depends on what kind of contributors you work with, but it's certainly a problem. Rust can help here though, because the thing is, Rust can give us a lot of tools that allows us to enforce things that we would have had to have done over email ourselves. And this is something that is a lot more capable than anything we were really ever able to do in C. So type state patterns like the atomic commit tail are a really good example of this. A lot of times they have little, usually no runtime cost. And the thing is, the upfront cost in sort of figuring this out is large because there's a pretty big learning curve and you sort of have to really rethink how you write a lot of your code. But the potential for this saving time long term is kind of astounding. Of course, a lot of people wonder, what about unsafe code? But in my experience, this doesn't end up changing things very much. A lot of the time, even with unsafe code, for one, unsafe code actually sort of also acts as an enforcement tool, because if you have something that the compiler isn't able to actually type or check itself, you're able to write what's called a safety contract. And if you try to do unsafe code without providing a safety comment, the compiler will actually complain at you. So you're sort of forcing people to actually write down the logic that they're following when they're doing something that might violate the invariance of the language. And this is really useful because it gives maintainers and reviewers something to actually look over to verify whether what the person is doing is making sense. And it's sort of wild what the end result of this is. Because in writing Rvkms, I spent almost no real time on debugging. I think I could probably say I spent only around like 24 hours total, and this was work over the course of a couple of months. So it's kind of impressive because almost every time I've written a driver, it's sort of gone like this. You write a bunch of changes that make sense and are sound, but then you end up spending the next day, sometimes even multiple days, debugging subtle errors all over the place. Maybe you forgot to check something for null. Maybe you forgot to initialize something. Maybe you forgot to make sure that something was thread safe. And this process sort of repeats itself as you're writing a driver in C. But over Rust, it kind of doesn't. If things compile, a lot of times it will actually work, which is a very weird concept, and it's almost unbelievable until you've actually dealt with it yourself. So before I worked with Rust, I was kind of off-put by a lot of the patterns that you would see. Things like not having null, for instance. Like, oh, I have to handle both conditions every time. What if I know something's not going to be null? And tons of types, that sounds kind of like a nightmare. But Rust is ergonomic enough that you almost barely think about this stuff a lot of the time once you've actually finished designing your bindings. And not even that, it also almost feels obvious what the right design is a lot of the time. Just about every construct that Rust is forcing you to deal with, it has almost a million different shortcuts for actually making it as legible and simple as possible. And a lot of the time, you're not even like, once you're past the actual stage of developing bindings or APIs and so forth, you're not even really thinking about this stuff afterwards. A lot of the time, the language just sort of handles it for you. I think as well, too, something that's nice to mention is the scope's a lot smaller than it seems. I see a lot of people make comparisons, C++ versus Rust, but I don't really like these because Rust is kind of a shockingly small language. It definitely is complicated to wrap your head around at first, but you can certainly tell the scope is pretty limited. Whereas a lot of languages like C++, they're okay, but a lot of times they feel more like a framework than a language. And a lot of the stdlib sort of comes from the same KISS philosophy that C standard libraries tried to do, but it's continually being iterated on, not in a way that makes it difficult to maintain compatibility per se, but like in a way that actually just makes things easier to work with and less troublesome. And a lot of times, too, what this leads to is there's usually not a whole ton of different ways to actually do something in this language. So once you actually get used to Rust, the correct way of doing stuff almost always feels obvious. So that sort of leaves me with one last question. Would you rather repeat yourself in a mailing list a million times to stop people from making the same mistakes in their code using your mail client, or would you just rather have the compiler do it? So give Rust a try. So any questions?
Hi. On the topic of Rust as a maintainer, how do you see Rust's role as API evolves, where you have more than one correct way of doing things?
Do you mean like Rust's API or
No,
what?
the API of DRM evolves, right?
Yeah, honestly, I think it's not too difficult to work with. I have found that refactoring Rust code tends to be very easy, even with a lot of more, like subtly more complicated changes than you might have to work around in C. There's still obviously some overhead there. It's not free, but like I think more often than not, a lot of times it's not too difficult to actually fix things later on. Of course, obviously the goal is to avoid that, but yeah, I think it works generally just as well as C would for that sort of thing.
No, the question is on if the API for DRM changes, where you have different ways that are both correct. You said some of the code doesn't even compile nowadays if you don't do all the stuff.
Oh, yeah, I mean, so the point of that is mostly like, because the thing is, it doesn't compile if you take all the steps, but we're limiting that to a subset of steps that make sense for any driver, regardless of use case.
Yes.
And most of this is sort of things that we already have as requirements. So it's not necessarily that we're like limiting if a driver needs to take extra steps, because the way I tried to design all of this is so that we can expand upon it in the future. Like, for instance, with having to control the order of operations in which you might have to update CRTCs is a pretty good example. It's not something we support now, but actually adding support for it and still maintaining that sort of compile time checking is actually pretty simple. It just sort of means being careful when you actually make those APIs to make sure, that you leave room for things to actually be added in the future without necessarily constraining people and stopping them from being able to do that.
Okay, thanks.
In working on the Rust bindings, were there like a number of cases where it was beneficial to the C code because you found things in doing the work that was broken in C, and would thus be having Rust equivalent of a lot of the C code would make the C code better just by being another way to check it?
Definitely. Actually, I feel like I got a little lucky here because for the most part, DRM is surprisingly well defined, but it sort of became obvious that exactly what you said, sort of using it as a tool to verify C code is correct. I definitely run into this in other areas of the kernel where you would find certain areas where, for instance, you realize, oh, there's no locking here. They just sort of rely on, say, driver initialization being a single threaded context or that sort of thing. So I definitely think it's a very useful tool towards that goal, because it does definitely sort of force you to actually sit down and codify all of these things. And it very obviously points out like things where this was never actually codified and we sort of in C just managed to avoid it running into problems. But yeah, we definitely ran into that a few times.
Apologies if the question won't make much sense. I'm only briefly familiar with the stuff that you talked about, and I didn't understand half of the talk. And but the question is like, it seems that you've been struggling a lot with the current, you're limited by the current drivers, like APIs and data models that they have, and the Rust kind of by its structure imposes certain limitation of what you can and can't do. And I wonder, have you thought about like, if you could ideally, like it's not practical, obviously, just completely not think about what current drivers do, and how would you design the whole like DRM stuff from scratch given the like Rust requirements?
A little bit, but I've sort of found, and that was sort of what I was getting at before, with DRM being well defined, that like surprisingly, even though some of this was challenging to sort of figure out the bindings for, I didn't run into a whole ton of situations, actually pretty much ever, where something was actually impossible. And a lot of this is sort of helped by the fact that like DRM is pretty well documented, especially in terms of like locking and that sort of thing. And most of the cases where you would typically run into problems in other parts of the kernel. So I feel like that hasn't necessarily been necessary, mainly because of the care that was taken with a lot of DRM. So yeah.
Thank you.
No problem.
Interesting talk. I need to get a bit more into Rust and learn more, but in your opinion, I've seen a lot of talk about Rust for like sort of new components or things that are disjointed from existing code. But does it make sense at all for like features that one would add to DRM, like the color pipeline API, for example, now that's blowing up on Xavier's desktop with null pointers that I haven't seen with my IGT tests, but I haven't done enough end-to-end tests. Would it make sense to do that, or would it be a lot of overhead and creating bindings, etc.?
I actually think it would, because I mean, I think the thing is, even though like the main difference is Rust forces you to think about this stuff up front before you can really get something working. So at first, a lot of the time, it seems like, oh, wow, this is a lot of work and overhead, and I'd rather just sit down and do this in C, right? But like, a lot of the time, the things that Rust is forcing you to think about upfront are things you're going to eventually have to think about anyway. And the advantage of actually doing all of this stuff upfront is that once you actually manage to come up with something that it looks like where it would actually work, it usually does. And you end up spending more time sort of figuring out the actual hard design problems than you actually do, chasing down all the references or that sort of thing. So I think it'd actually be a pretty big help if we were able to get bindings generally far enough that we would actually have the infrastructure to be able to implement support for that sort of thing.
So pretty much it forces you to be a bit more honest up front rather than say, it works, and deal with it later.
Exactly, yeah. I think the one challenge would be figuring out how we can extend that to drivers written in C, because unfortunately the one thing that is a little difficult is actually interfacing with Rust code from the C side. But I think that's something we might be able to do in the future, or yeah. But I definitely do think it is a generally good idea.
Thanks.
No problem.
Right, I have one about object lifetimes, which is kind of adjacent to memory management, which proposed not to talk about. But to preface this, my KMS is a bit rusty. It's been 5 years since I worked on KMS side of things in DRM. But I have a vague recollection of some object lifetimes being non-composable. The borrow checker being quite a big constraint on how you handle lifetimes. How does that work when one sub-object has to outlive its, enclosing scope?
That was mainly what the static mode object stuff was for, because that was actually one of the big challenges that we ran into, where what usually ends up happening is the way that you deal with it is everything maps to some sort of lifetime. Sometimes it's not necessarily lifetime of the object you're working with, but for instance, with static mode objects, the closest lifetime we could map to was the one for the device.
Right.
So a lot of times you just sort of have to trace that path because everything's going to have some sort of lifetime, and it's sort of just figuring out how to map that to a specific resource and sort of make that work in a way where, it's basically pretend ref counting, where you're taking a ref count of something else in order to keep the object alive. And that seems to actually work pretty well.
Right, so you force it back into a composable structure, basically.
Pretty much, yeah. And for objects where, that's sort of where the type state patterns come in as well, for objects that you can only really compose early on in the driver initialization process. You can sort of use having different types of devices and that sort of thing to constrain it there so that you don't really have to worry about that later on.
Right. Thanks.
No problem.
I had sort of a more specific follow-on question to the question earlier about where if you started from a blank slate, could you get a better design? Are you happy with the ref cell design you came up with to handle all the borrows and stuff you couldn't work out with the atomic state objects? Or do you think if you started from a blank slate, you could move that back up to compile time and make it a little cleaner?
I actually think I am pretty happy with it. It's a little bit of a shame that we have to do some of that at runtime, but a lot of that really just comes down to maintaining a single bit mask of objects that you've taken out. So I think overall it actually works surprisingly well. So I'd actually say I'm pretty happy with it.
So if you're not experienced with either Rust or KMS drivers, you probably still want to start with C to get something working. What do you think?
For the time being, I would say probably yes, but that certainly might change in the future. The only reason I really say so right now to start off in C is mainly the issue of bindings not being there. Because pretty much every time I've had to add some sort of feature to Rvkms, it's been, okay, now I have to write these bindings as well, which usually doesn't just mean knowing Rust or C, but also having a pretty deep understanding of how a lot of lifetimes and synchronization in DRM actually works. So I think if you're just starting off from scratch, right now it's probably better to do it in C, but that certainly might change in the future as this becomes more fleshed out.
Thank you.
Apologies. Quick question. How are you happy with Rust compile lifetimes regarding to kernel level projects? Because usually like with bigger projects outside of kernel, it's like I'm very unhappy about it.
You mean Rust like in terms of like lifetimes?
No. I mean like compile time, like how much time it takes to compile.
Gotcha. Actually surprisingly happy with it. But I will say I feel like it's a little too early for us to really tell. As we get more drivers written in Rust, I think that's really when we're going to start to figure out how difficult the compile time is, because it may certainly get larger or longer as we actually add more code.
Thank you.